So here is our neuron. Up here we have our dendrites, and then our cell body here in red, and that's going to be our receptive segment. And we're going to see chemically gated cation channels that allow both sodium and potassium to pass through. And then there's also chemically gated potassium channels and chemically gated chloride channels up here in our receptive segment. Then our initial segment here in orange is going to have our axon hillock. And there we're going to see voltage-gated sodium channels and voltage-gated potassium channels. And then for our conductive segment, that's our axon here in green. And there we have voltage-gated sodium channels and voltage-gated potassium channels as well. And then in blue, our synaptic knobs down here is our transmissive segment. There we have some voltage-gated calcium channels and calcium pumps. And then throughout the whole neuron, we have potassium leak channels, sodium leak channels, and then sodium-potassium pumps throughout this entire cell, or the entire neuron. Down here I have another neuron drawn, and that's up here too. So the synaptic knobs of this neuron do not directly connect with maybe the dendrites of this other neuron. There is a little bit of space there, and same up here. There is a little bit of space between our synaptic knob of this neuron and the dendrites of this one. That fluid-filled space is going to be our synaptic cleft. So when neurotransmitter is released from this presynaptic neuron, it's going to flow through the synaptic knob, be released from the synaptic knob of that neuron, and diffuse through the synaptic cleft, that fluid-filled space, and then it will connect. It will bind to our chemically gated cation channels here in our dendrites in the receptive segment, and that will allow sodium to flow into the cell, creating a local current. Those currents are very short-lived. They only last as long as the chemically gated cation channels are open. If they're closed, the local current stops. And then if we have a stronger stimulus, it will cause more of those chemically gated cation channels to open. So we have all of our open channels here. And that's going to allow more sodium to flow into the cell, creating a greater current, a greater flow of sodium. In our receptive segment, when we're getting that sodium coming in, those local currents, we get graded potentials. Here I have an excitatory postsynaptic potential, or EPSP. Those are going to cause membrane potential and our voltage to kind of be more positive. It's going to bring membrane potential towards threshold. And then maybe down here, when our chemically gated potassium channels are open, potassium is going to flow out of the cell. And that's called an inhibitory postsynaptic potential. It's bringing membrane potential further from threshold. And then down here, so that's our neurotransmitter is going to diffuse through here until it reaches our axon hillock in the initial segment. And there is where summation occurs. We are going to add together our excitatory postsynaptic potentials and our inhibitory postsynaptic potentials. And I like to think of this as like math. Like if this is more positive, maybe that's a +2, and maybe our inhibitory is a -2. If those two reach the initial segment at the same time, they're just going to cancel each other out. Like a +2 plus a -2, it's just going to be 0, and membrane potential stays the same. But if we get multiple excitatory postsynaptic potentials, it's going to raise membrane potential. It's going to be more positive. Maybe that's a +2 and a +2. It's going to bring our voltage closer to where it needs to be to reach threshold for our action potential to take off. So in our initial segment, we're adding together those potentials. and we're going to see some voltage-gated potassium channels and voltage-gated sodium channels that are stimulated to open. When we reach threshold, sodium channels are opening, and we have enough of these excitatory postsynaptic potentials that's going to reach threshold. When that happens, our action potential is propagated down the axon in the conductive segment. And there we're going to see sodium channels opening. The voltage-gated sodium channels are opening and allowing sodium to move into our cell. And that is going to bring membrane potential to skyrocket, and that's what we see here when we look at our graph in a second. That is the depolarization, is when sodium is rushing into our neuron in the conductive segment. And then our book describes it as a domino effect. I like to think of it more like a wave. Immediately following these sodium channels opening, these voltage-gated potassium channels are going to open, and that will allow potassium to move out of the cell. And there we're going to see membrane potential drop back down in repolarization. So that is allowing our action potential to be propagated down our conductive segment into our transmissive segment. Here, the voltage change up here from the conductive segment is going to stimulate our calcium pumps to start pumping out calcium here into our interstitial fluid. And then that's creating a calcium concentration gradient. And when we reach our transmissive segment, the calcium will move down its concentration gradient back into our neuron, into the synaptic knobs through the voltage-gated calcium channels. Down here, mainly what's happening is neurotransmitter will be released from the synaptic knobs. So our calcium coming in from our voltage-gated calcium channels will fuse to or bind to the synaptic vesicles in our synaptic knobs here. And that allows the vesicles to interact with our plasma membrane of the synaptic knob. And then through the process of exocytosis, the neurotransmitter is going to be released from the synaptic knob, where it will diffuse across our synaptic cleft, and then eventually bind to other channels here, maybe in our other neuron, the dendrites of this neuron have all the same channels that we saw up here in these. So our neurotransmitter will diffuse through the synaptic cleft and bind to those channels here, or it could be going to an effector organ. And then we're going to take a look at what's going on with membrane potential. Our graph here, I don't need that one. Okay, so we're going to be taking a look at what happens with membrane potential while all of this is happening. Here we have in column 1, it's just at resting membrane potential at -70. No communication is coming into the cell. All of our channels in our dendrites and the receptive segment are closed, and no neurotransmitter is entering our neuron. And then we move on to column 2 in our initial segment. This is where summation is going on, where we're getting those inhibitory postsynaptic potentials and the excitatory postsynaptic potentials. When those voltage-gated sodium channels are opening, for our excitatory postsynaptic potentials, we can see that brings membrane potential closer to threshold a little bit, to be a little more positive. And then we see that here, it's bringing membrane potential towards threshold. And then our inhibitory is going to bring membrane potential a little bit further away from threshold. It's going to make a more negative voltage on our membrane. And that's in column 2. That's going on in our initial segment. Those voltage-gated sodium channels are opening, or the voltage-gated potassium channels are opening during summation. If we get a strong enough stimulus and excitatory postsynaptic potentials are stronger than our inhibitory postsynaptic potentials, or we're just going to add those together and it's going to bring membrane potential towards threshold. Now, once we reach threshold, in our initial segment, it's going to propagate our action potential down the conductive segment, and that's what's happening here in column 3. Our action potential has been propagated down the conductive segment, and we're going to see the voltage-gated sodium channels opening to allow sodium to flow into our neuron, and that is going to be depolarization. That's where we see our action potential take off here and become way more positive than it was down here, maybe at resting membrane potential, or compared to our threshold, maybe at negative 55. And then again, our book described it as a domino effect. I just think of it as a wave. Immediately following these voltage-gated sodium channels opening, voltage-gated potassium channels are going to open right after that, and potassium is going to flow out of our cell, and that is what we see in column 4. That is when our voltage-gated potassium channels are opening to allow potassium to flow out. That is going to be repolarization there in our conductive segment. And then in column 5, this is where our potassium channels over here in our conductive segment actually stay open just a little bit too long and let just a little bit too much potassium leave the neuron. So we get this little dip here, this little hole. It's going to go a little bit below resting membrane potential, and that is called hyperpolarization. And then here in column 6, that is where we see those NAK pumps working that I mentioned were throughout our entire cell. That's going to help bring our sodium and potassium levels back to normal. It's going to bring us back to resting membrane potential. Okay, so our brachial plexus is a network of nerves that supply the upper limbs, and it kind of has a pyramid of organization. So trunks are split into anterior and posterior divisions, and those divisions are split into cords, which I have here in purple. We have our lateral cord, our medial cord, and then our posterior cord, which is going to get more posterior muscles. And then this is all very branching, so it can branch out here, and then it kind of branches back together for our medial nerve. But first we have our auxiliary nerve, and that is innervated by the posterior cord, and that's going to get your teres minor, and then some of your deltoid is going to be innervated, and then for sensory information, that's going to be picked up from the deltoid. And then our median nerve is made from the innervated from the lateral cord and the medial cord, and that kind of branches back together and gets down the median of your arm. So that's gonna innervate our flexor pollicis longus and our lateral flexor digitoris profundus, and then it's going to innervate some of these lateral fingers down here, the lateral 3.5. So your thumb, your pointer finger, your middle finger, and then half of your ring finger. And we kind of see that whenever you go to flex those 3, your ring finger kind of flexes along with it. And sensory information is picked up from those 3.5 fingers. And then next we have our musculocutaneous nerve, and that is innervated by the lateral nerve up here, So that's going to get muscles like our biceps brachii. And as we know, when we flex with force, that's what flexes our arm, is the biceps brachii. And sensory information is picked up down here in our forearm. So a little bit here in the anterior side, and then a little bit back here on the posterior side. And then our radial nerve is made with our lateral head of the triceps brachii. That's over here. The lateral head of our triceps brachii, and then the long head of the triceps brachii. And that is innervated by the posterior cord, which ran kind of back in the posterior side of the arm. And sensory information is going to be picked up from most of your upper arm, and then down your forearm, and some of the fingers on your posterior side when we're in anatomical position. So your thumb, your pointer, and then middle fingers. And then our ulnar nerve. Our ulnar nerve is innervated by the medial cord here, and that is going to get muscles like down here in your forearm. It's going to get the flexor capri ulnaris, and then into our palmar intrinsic hand muscles. Sensory information is picked up from your medial 1.5 digits down here, so like your pinky, and then part of your ring finger as well down there. All right, we're gonna take a look at our brains. Here we have our cerebral cortex outlined in this light blue. That's just like a coating of tissue that wraps around your entire brain, and then that has its different lobes for it. The frontal lobe, the parietal lobe, the occipital lobe, and the temporal lobe. Those have their own functions. And then here is the diencephalon, and just below that is where our brainstem sits. For that, we have our midbrain, our pons, our medulla, and that leads into our spinal cord. This is kind of like a relay center. I think of it like a phone center where you call and then they'll connect you to whoever you're trying to call. But that functions in connecting your brain to the rest of your body, and then the rest of your body to your brain. And then for these different lobes of our cerebral cortex, those have their own functions as well. For our frontal lobe, that's going to sit in the front of your brain, about right there. That functions in concentration, decision-making, planning, things like that. And then at the central sulcus is where our parietal lobe begins. That's going to sit about right here. That is involved with sensory information coming in, like the shape of something, the texture of something. When you're looking at it, we know that this is probably hard, whereas when we're looking at a liquid, we know that's not going to be like plastic. And then just below that, at the parieto-occipital sulcus, we have the occipital lobe back here. Sits at the back of your brain. That is involved with processing visual information as well. That's going to store visual memories. It's going to look at the color of things. It's going to look at movement of something when you're looking at it, if something's moving. And then it's going to store those visual memories. And then for our temporal lobe, that sits behind your ears here, on either side of your brain stem. Sits about right there. That is involved, that starts at the lateral sulcus. It sits at kind of the bottom of your brain. And that is involved with sensory information as well. Things like hearing, smell, the position of your body, where it's at, things like that. Okay, now we are talking about nerves in our lower limbs. In our lumbar plexus, we have our femoral nerve, and that's going to be, it starts up here in your hip extensors, and that's coming from L2, L3, and L4. And the femoral nerve is very branching to get all of these muscles, so it's going to innervate your quadriceps femoris up here and anterior thigh muscles, and then sensory information is picked up from those same areas up here in our anterior thigh, as well as some medial leg muscles down there. Now for our tibial nerve, that's going to be coming from L4 through S3, and that's going to get posterior thigh muscles. So back here in our biceps femoris long head there in our upper thigh muscles back here. And then it's going to run down our leg and get muscles like our flexor digitorum longus. And for that sensory information, your tibial nerve runs into the bottom of your foot, and that's where sensory information is picked up. Next, we're going to talk about our common fibular nerve, and that will innervate muscles here in our biceps femoris short head, and then this nerve splits into our deep fibular nerve and our superficial fibular nerve. In our deep fibular nerve, that's going to get muscles like our tibialis anterior, and then it will run down and get some of our extensor digitorum brevis muscles here in the top of our foot, and sensory information is going to run down this nerve and is picked up from the dorsum space in between our first and second toes. And then for our superficial fibular nerve, that is going to innervate muscles like our fibularis longus here, and that will also run down into the dorsum of your foot, and that's where sensory information is picked up in the top of your foot, the dorsum of your foot there.